Okay, so where we left off, we were talking about how I don't like memorizing things. If I can avoid it, I will. So if I can narrow all of the formulas in chapter 6, because there's a lot, um, I'm going to try to get everything narrowed down to just the two. All right, so the two formulas, again, I've got highlighted. The P1V1 over T1 equals P2V2 over T2. That's our formula for any kind of change in conditions, change in temperature, change in pressure, something like that. And then the other formula is the PV equals nRT, which I always call PIVNERT, but it is the ideal gas law. We'll talk about ideal gases more towards the end of the chapter, but this is our relationship of pressure, volume, temperature to the actual quantity of gas that's in the sample. And to a chemist, right, that quantity, which is, you know, always good to know, is the moles, right? That's our center point. So you'll see N is for moles. R is the constant that puts it all together. So I need you to memorize the two formulas and the gas constant, 0.08206 liter atmosphere per mole Kelvin. And then just remember that because of that R constant, the units are very picky for PIVNERT. You know, volume has to be in liters, pressure has to be in atmospheres. So let's look at another example. It says, how many grams of nitrogen gas are there in a sample that occupies 35.0 liters at a pressure of 3.15 atm and a temperature of 852 Kelvin? So we've got a volume, a pressure, a temperature, but nothing's changing, right? There's no change in volume, no change in pressure, no change in temperature. So that's what I was talking about. Since there's no change in conditions, the P1V1 over T1 formula is not going to be the right one, right? Because we don't have a V1 and a V2. We don't have a T1 and a T2. We just have one volume, one pressure, one temperature. The other thing that we have going for us here is that it's looking at the grams of the gas. And so if we want grams, just know that that is something we should be able to easily do if we know moles, right? So if we can find moles using PV equals nRT, then we can easily convert that to grams using molar mass. The other thing that's going to come up quite a bit in this chapter is Hofbrinkel. So you want to remember that with those 7 elements, like in this case, when it just says nitrogen gas, really what that means is N2. All right, if it said hydrogen gas, H2, oxygen gas, O2. All right, so that again, that's part of the Hofbrinkel. And I think I mentioned this when we learned it. There are the 7 diatomic elements. To me, it looks, the way I memorized it, I didn't know Hofbrinkel, but I've heard it since I started teaching, and I'm like, oh, that's very helpful. I learned it like they make a 7 on the periodic table. So that's how I learned it. And of course, hydrogen is kind of off at the side, but those are the 7. That's how I remembered it. But you do it however, Hofbrinkel's much easier, but that's how I looked at it. Okay, so we have a PIVNERT question this time because one volume, one pressure, one temperature, and then we want to relate that to moles, but then take it to mass. So we're going to, again, I line everything up. I've picked my formula. My pressure is 3.15 atm. My volume is 35.0 liters. N is what we're going to be looking for. R is a constant. It's always 0.08206 liter atmosphere per mole Kelvin, and temperature 852 Kelvin. Okay, so I got everything lined up. With PIVNERT, what's really important is that you double check the units. The units, again, really picky. So are my units correct, right? Volume has to be in liters. Good. Pressure has to be in ATM. Check. Temperature always has to be in Kelvin. Good. So we don't have to do any unit work up front, which is nice. We're just going to solve for moles. So I'm going to take my formula. I'm going to divide both sides by RT. So PV divided by RT is going to get me to moles. And then I can plug everything in. All right. So pressure, 3.15 atmospheres. Volume, oops, sorry, my recording just converted from the first session. So we got 35.0 liters. R, 0.08206. I'm going to leave the units out just because I already wrote them. I don't want to have to write them again. All right, and then temperature 852 Kelvin. All right, so I have 3.15 times 35.0, divide by 0.08206, and then divide that by 852. And what I get here to three significant figures is 1.58, and the unit would be moles. That would be how many moles of nitrogen were in this container. So again, like we were talking about at the very beginning of the chapter, in order to understand how many particles are in the sample, we can't just know the volume, because the volume, remember, for a gas is flexible. It's not like volume of a solid that's fixed. It's flexible. So the volume can change, but you still have the same number of particles inside. So we have a lot more information we got to know. We also have to know, okay, what temperature are we at and what pressure are we at? If we know all three of those, then we can figure out how many particles are in the sample. So I now know how many moles of N2 I have, because that was N, and that's what PivNert allows me to calculate. And then if I want to take it to mass, I'm going to do N and multiply it by molar mass, and that will get me to mass. So for the periodic table, just remember again, nitrogen is diatomic. So N2, nitrogen is 14.01 times 2 would be 28.02. That would be the molar mass of nitrogen. So I've got the 1.58, multiply it by 28.02, keeping 3 sig figs, I get 44.3 grams of nitrogen. So that would be the mass of nitrogen in my sample. All right, so a little bit different of a calculation, because in this case, we hadn't seen this yet, no change in conditions, right? So we are just looking at using the ideal gas law formula. So we're going to do another one and see what we think. The question says, what would be the temperature in Celsius when 15 grams of oxygen exerts a pressure of 785 torr when it's in a volume of a 5-liter container? So again, what I'm looking at here is I only have one volume, I only have one pressure, and I have mass, and I want to know temperature. So again, there's no change in volume, there's no change in pressure. It's a snapshot. We're just looking at this sample at these conditions, go, right? That's where your PV equals nRT formula comes in. Like we talked about with the last example, just know that it gives you mass, and if mass is given, we can easily convert that to moles. So if you have a question that gives you the mass or the moles of the gas present, or it's asking you for the mass or the moles of the gas present, more than likely it's going to be a PivNert question. Or it may be stoichiometry, but still that will go through PivNert. All right, so I've got pressure of 785 torr, volume of 5.00 liters, N is 15.0 grams, but we need to change that to moles using molar mass. Oxygen, again, one of the diatomics, part of Hofbrinkel. So 16 times 2 would be a molar mass of 32.00. All right, I'll come back to that. R, always 0.08, 206, liter, atmosphere, per mole, Kelvin. And then temperature is our unknown. That's what we're trying to look for. All right, so let me lift that up a little bit. Okay, so again, with PivNert, the units are picky. So I'm going to check my units first. Volume has to be in liters, which it is, so we're good there. But pressure has to be in atmospheres, which it is not. So this is that one conversion I want you to remember, which is 1 atmosphere is 760 torr. So if I take 785, divide by 760, the 760 is an exact value, so don't let that limit the sig figs. Go with the measurement, which had 3. So when I convert it to 3 sig figs, I get 1.03 ATM. All right, so there's my pressure on the atmosphere scale. And then just really quick, 15 divided by 32, I really have 0.469 moles of O2. All right, so we've got pressure, volume, moles, R, solving for temperature. So we have PV equals nRT. We're going to divide both sides by nR. So when we solve for temperature, PV divided by nR, that'll be temperature. So plugging everything in, pressure in atmospheres, 1.03, volume in liters, 5 liters, moles first, 0.469, R 0.08206. Again, I'm going to leave off the units just because running out of room. All right, so I got 1.03 times 5.00, divide that by 0.469, and then divide that by 0.08206. Keeping 3 sig figs, I get 134. And the question is, it's a temperature, so what's the unit? And we know because we use this R constant and because it's temperature, it's gases, it's got to be Kelvin. Now, just look for this on the quiz because this happens a couple of times. It's asking you per Celsius. So just make sure we do one more additional step here because like I said, this is on the quiz. We're going to take that Kelvin, subtract the 273.15. And when I take 134 minus the 273.15 and I keep it to the ones place, I get negative 139 degrees Celsius. So that would be the temperature of my oxygen gas under those conditions. All right. So again, the last 2 examples we didn't heat the gas, we didn't squeeze the volume, we didn't change the pressure, so we knew it was a Pivnert formula. And then what was also different is that in both of them, we were looking at the quantity of the gas, either trying to figure out what mass of it we had, or we were given the mass and we were looking for a different variable. But in both cases, the quantity of gas was part of the equation. All right. And by quantity, I mean mass or moles. All right. So now if we keep going, we have some stoichiometry to talk about. We've got density and molar mass. So Avogadro's law came up earlier in a question in the part 1 video. So Avogadro actually didn't come up with the 6.022 times 10 to the 23rd. His work was actually in gases. And it makes total sense. He said that if I have a container of gas and another container of gas, and I think that looks fairly good. The 2 containers have the same volume, same pressure, same temperature. So these 2 samples, right, they're kept under the same pressure, same volume containers, same temperature on the same, like on the same shelf in the lab room. His idea is that if they have the same pressure, temperature, and volume, there should be exactly the same number of molecules inside both of those samples. That was Avogadro's theory. And that is what led to the discovery of this constant, like this mole, and it led to the 6.022 times 10 to the 23rd. But really, he had nothing to do with that particular number. That came later. So he later, if you look at Pivnert, this is really what should be Avogadro's number. It's this 22.4, but they didn't ask me. If I use Pivnert, the ideal gas law, and I plug in standard pressure, which is 1 atm, and a volume unknown, 1 mole of gas, R 0.08206, and standard temperature of 273, I would solve for volume and get 22.4. So Avogadro's law or number is that as long as I'm under STP conditions, which means standard temperature, standard pressure. So standard pressure, again, defined as 1 atmosphere, that is standard pressure. We're at sea level, we're right around 1 atmosphere. We're like slightly a little bit over that depending on the weather, but we're basically right at 1 atm. Standard temperature, not sure why 0 degrees Celsius is standard, but it is what it is. So 273 Kelvin is the standard, 1 atm standard pressure. So if I have these 2 containers, right, and they're both at 1 atmosphere pressure, 273 Kelvin. If they both have the same volume of 22.4 liters, then both of them would contain exactly 1 mole of gas. But that 22.4, right, that's coming from PV equals nRT. So again, if I plug in standard pressure of 1 atm, volume would be my unknown. We're assuming 1 mole of gas, 0.08206 for the constant, and standard temperature of 273. When I do that, that's where that volume of 22.4 comes from. And because it's in Pivnert, right, the unit then would be liters. So that's where that number's coming from. All right, so that's really Avogadro's number. But anyway, so when is this helpful? Honestly, it's not helpful that often unless you're at STP. That's the only problem with this number. It's a nice number. It can be a nice little shortcut if we're doing stoichiometry or any kind of conversions between moles and volume. But the problem is that number is only true if we are under conditions of standard temperature and pressure. And if you can imagine, we're not always going to be under those conditions. So if we change the pressure, that changes the volume. And if we change the temperature, that changes the volume. So 22.4, it's constant, but not really, only if you have STP conditions. So you have to make sure and look for that code, STP. So like, here's an example. What's the mass of propane? And if it were a test or a quiz, just know I would tell you propane is C3H8. We don't need to know what that is. And here's where I recognize that I've got STP. So I've got this propane, 50 liters of it. It's under standard temperature and pressure. If you want to memorize the 22.4, go for it. If you don't want to memorize it because you're like me and you hate memorizing things, you don't need to. Because if I dissect this, like we talked about on the last example, if we're looking for mass, we can get moles first, right? We've got our volume of 50.0 liters. If it tells us STP, then that's telling us the temperature is 273 and the pressure is 1 atm. So with the test, I won't give you the 22.4 because you don't need it, but I will give you the definition of STP just to make sure we remember. So on the test, it'll say STP means 1 atm and it means 273 Kelvin. So I know when this question says we have this gas at STP, I know that really what that's encoding in the question is that my temperature is 273 Kelvin and my pressure is 1 atmosphere. All right. So that's what that code means. So if I look at this now, I've got a volume, I've got a temperature, I've got a pressure, no change in conditions. I'm looking for quantity. So it's going to be PV equals nRT. So I'm solving for N, pressure, standard 1 atm, volume was given at 50 liters, N is going to be what I'm looking for, and temperature will be 273 because again, that's standard. All right, and R of course 0.08206. So I'm going to take PV divided by RT to get moles, pressure again 1 atm, volume 50 liters, R 0.08206, and temperature 273. All right, that'll again get us moles. So I got 50 liters divided by 0.08206 divided by 273. So I have 2.23 moles of C3H8 propane. Then the question is, okay, well, what mass would that be? All right, so we've saw this before with the nitrogen. You have to multiply by the molar mass. So if I add up 3 carbons and 8 hydrogens, I get 44.11. For some reason, my memory doesn't want to say that that looks right. Yep, that's right. And that would be the molar mass of C3H8. So if I multiply the molar mass times the 2.23 moles, keep 3 sig figs, I have 98.4 grams of the C3H8 in that 50 liter container sample at STP. Oh, it froze up again really quick. All right, so if you wanted to do a slight shortcut here, you could, but this shortcut would require you to remember 22.4. And I never really saw the point of that because number one, I think I've mentioned this, I don't like memorizing things. So you'd have to memorize another number, which I'd rather not do. And that number, remember, it just comes right from Pivnert. And I already know Pivnert. So that's why in this chapter, I like to just kind of narrow it down as much as possible in terms of the memorizing and say, okay, I'm either going to know to use P1V1 over T1 equals P2V2 over T2, or I know I'm going to use PV equals nRT. Remember that STP definition, that'll be given. So I don't have to memorize that. So when I see this question, it says, okay, what's the mass of propane? Remember, I'll give you C3H8. I've got a volume. Coded in STP is my temperature and pressure, right? That'll be given to me on the test, right? So remember STP definition, that will be given. Then all I have to think about is, okay, I'm going to use PivNerd. If I wanted to maybe think about using a shortcut here, again, I don't see it as a shortcut, but if I did, what I could do here is I could say, okay, I got 50 liters, 1 mole of any gas at STP, again, it only works if we're at STP, is 22.4 liters. That's Avogadro's number. And then for 1 mole of propane, I have a molar mass of 44.11 grams, right? So it seems shorter. The problem is you'd have to memorize the 22.4. But remember, that number just came from using PivNerd. So to me, it seems easier just to use PivNerd. But if you think it's easier to do this and memorize one more number, go for it, because that also will work. So anytime you see a question that tells you that you're at STP, what really is coded in there is your temperature and your pressure. You're at standard temperature, which is always defined as 273, and you're at standard pressure, which is always defined at 1 atm. Now, the 1 atm is a perfect one. It won't limit your sig figs. So don't, if anybody in here was thinking, well, wait, shouldn't there only be 1 sig figs? This should really be 1.00000, right? We're not going to do that. We're just going to put 1. So it doesn't limit sig figs. Same with the temperature of 273. So we'll just look at whatever the measurement given it in the question, 50.0, that had 3 sig figs. Okay, so density of gases. We're going to look at density of gases and molar mass of gases. Now, density, we know from chapter 1, density is mass over volume. What's interesting about these questions is a lot of times it'll say something like, determine the density of oxygen gas at a pressure of 1.5 atmospheres and a temperature of 300 Kelvin. And you're like, okay, well, density, I need a mass and a volume. And this question gave me neither of those two things. So then you're like, how do I do this? So again, pick your formula. Are we going to be using P1V1? Or are we going to be using PivNerd? If we're looking for the density of gas, we're looking at a certain set of conditions. We're not changing those conditions. We're looking at the density at this particular temperature or this particular pressure. So that means there's only one pressure, one temperature. So we are going to think about using PV equals nRT. All right. But then again, we're like, well, I need a mass and a volume for density. So how does this work? Okay, well, volume, I could see where that's going to come from using PivNerd. But then where does the mass come from? What you do is for these questions, you assume that N is equal to 1. In other words, you have 1 mole of gas. So N is going to just become 1. And then what that means is the mass is going to be equal to the molar mass from the periodic table. So in the book, it's going to give you a whole new formula. And again, I don't like memorizing formulas. So the way I look at this is to make it what I think is simpler is the density is mass over volume. That I already know. I've already memorized that. So what I'm thinking about here is because we're assuming 1 mole, my mass is going to be equal to the molar mass from the periodic table. The volume, right, would be, if I solved for volume, it would be RT divided by P. So that means in the denominator here, right, my volume would be RT divided by P, right? But if I divide by something and then divide by something, right, like 1 over the inverse of something, that means pressure really is going to move to the numerator, to the top. So density would be molar mass times the pressure divided by RT, right? And that's where this formula comes from. All right, now, if we are at STP conditions, which we typically are not, then we know that the volume of 1 mole of gas is always 22.4. And that's the formula we looked at in intro chem. So if that looks familiar, we did that in intro. But we're not going to be at STP here. We're in Chem 1, so we're taking it up a notch. So we're not going to be able to use that 22.4 anyway. Now, I usually do this in two pieces. So I'll show you what I mean by that. It says, let's look at the density of ethane, C2H6. Density of gases are typically in grams per liter instead of milliliters, just because they are mostly empty space. So typically your units are a little bit different for gases. You're at 25 degrees Celsius. You're at a pressure of 760 torr. So let's find the density. So we know for density, we need mass divided by volume. Again, for these questions, this is key. You have to assume that you have 1 mole of the gas, right? That means that the mass is equal to the molar mass, right? And we've got C2H6. So on my periodic table, I'd have 2 carbons, 24.02, 6 hydrogens, 6.06. So I get 30.08 grams. All right, then the second part is, what's the volume? And volume from Pivnert would be nRT over P. Volume, again, 1 mole, so it's going to cancel out. 0.08 to 06 for R. Temperature, 25 degrees Celsius, but again, for that, we add the 273 to go to Kelvin. So that's really 298 Kelvin. And then the pressure was 760 torr, but 760 torr is 1 ATM. And remember, for Pivnert, we've got to be an ATM. So we'd have 1 ATM here on the bottom. So the volume of this ethane, at least 1 mole of it, is 0.08 to 06 times 298. And I get 24.5 liters. All right. So now at this point, for this 1 mole of gas, under these conditions, I know that my mass is 30.08 grams for 1 mole. And I know my volume is 24.5 liters for 1 mole. So now I'm ready to solve. Density, mass over volume. Mass, 30.08 grams. Volume, 24.5 liters. I'll keep 3 significant figures. So 30.08 divided by 24.5. I get a density of 1.23 grams per liter. All right. So I like to do these kind of piece by piece by piece because, again, I don't want to have to memorize another formula. It's too easy for me on test day, especially, to put something in the wrong place. But this I know, like I know Pivnert, right? And all I have to make sure and remember, which is so key for these, is that if you're finding the density of a gas, make sure to remember that you have 1 mole of that gas. All right, so that means that the mass of the sample is just equal to the molar mass, right? That's very helpful. We just need the periodic table for that. And volume will come from Pivnert. And N basically cancels out because it's just 1, right? We've assumed it's 1 mole. So really what we're doing here is just multiplying R times T divided by pressure. Again, make sure you're in the Pivnert units using the 0.08 to 06. Now we know the mass and the volume, then we just divide. Mass divided by volume, there gives me my density. Now the follow-up question said, would the density be higher or lower at higher temperatures? And what we know is from Charles' law that if we increase temperature, right, the volume will increase. So then I think about the denominator here. If volume goes up, the denominator gets bigger. That means the density is going to go down. So density goes down when you're at higher temperatures. And the way I kind of thought about that was, if you're heating the gas, it's going to expand, which means you're going to have even more empty space. And so your density would drop. But it's really coming from that relationship that if you increase temperature, volume goes up. If your volume in the denominator is going up, that means your density should be going down. All right, so density would be lower at higher temperatures. All right, now in this question, the question was, well, what if you don't have 1 mole? What if you have a different? These questions are always going to be set up that you do the assumption that it's 1 mole. The thing is, density is constant. So as long as you're at the same temperature, I should say that, right? As long as you're in the same conditions, right? We're not changing the conditions, which we won't be. Your density would be the same if you have 1 mole of gas, or if you have 10 moles of gas, or if you have 1,000 moles of gas. Density would be the same. So that's why assuming 1 mole always works. And it makes it easy because the molar mass is just then the mass of the substance. So that's why we can always assume that we have just 1 mole. All right. Now, the other type of question that we had in intro, but was at STP. Now we're not going to be at STP is, all right, what if we want to find the molar mass of a gas? So if we want molar mass, again, some things to remember. Molar mass, if that's what we're solving for, is the mass divided by the moles, right? Now, in this case, we're not assuming 1 mole. So the mass isn't going to be because we don't know what the gas is. So we can't assume 1 mole and find the molar mass that way. Instead, we're going to be told the mass of gas in the sample, and we're going to have to then figure out, well, how many moles are present, and we'll have other pieces of information. So this is going to be equal to mass divided by N, where N is going to come from PV equals nRT. All right, so we're going to, again, kind of do this in 2 parts. We're going to first find the number of moles present based on the pressure, volume, and temperature that's given. And then we'll take the mass given divided by moles, and that'll get us our molar mass. So let's look at an example. Question says, let's find the molar mass of a gas if we have 0.440 grams at 179 milliliters, 741 millimeters of mercury, and 86 degrees Celsius. All right, so we only have 1 volume, 1 pressure, 1 temperature, and a mass. So again, if we're thinking about what unit or what formula to use, we're gonna pass through Pivner, right? There's no change in volume, no change in temperature, right? So Pivner is our formula. What's different is we want to know the molar mass. So just think, when you see that, you think grams divided by moles, because that's the unit, right, for molar mass. So the 0.440 grams is going to go in the numerator when we go to find the molar mass. So what we first need to find here is what is N, right? And that will come from PV equals nRT. So that'll be PV over RT. Now, some unit work. Because we're using R, volume has to be in liters. So I'm going to quick divide this by 1,000. So this is really 0.179 liters. All right, temperature, it is 86 degrees Celsius, but we're going to add the 273.15. So really this is 359 Kelvin. All right, and then pressure in millimeters of mercury. So just really quick up here, we're going to take the 741, divide it by 760, and that'll get us an ATM. So this is really 0.975 atmospheres. So now we have everything we need. Pressure, 0.975. Volume in liters, 0.179. R, 0.08, 206. Temperature in Kelvin, 359. So how many moles do we have in this sample, right? We know the volume of the sample, we know the pressure it's under, we know the temperature. So that should tell us how many moles or particles are inside. So 0.975 times 0.179, divide by 0.08206, and then divide that by 359. So I have 0.00592 moles of this gas present. Second part is to get molar mass, we need the grams of that gas in the sample, which was 0.440 grams, divided by the moles, 0.00592. So when I do that calculation, I get a molar mass of 74.3 grams per mole. So that would be whatever this unknown gas is, 74.3 grams. Now, more than likely, it's not an element, so it's not something I can go to the periodic table and figure out what it is. If it did say that it was like a diatomic, we might have more information to go on, but at this point, that's all we know. That's the molar mass of whatever this gas is. All right, so let's try another one. It says, let's find the molar mass again. It says liquid, but let's not be confused by that because it says it's being vaporized, which means that we're taking it and turning it into a gas. Okay, so you'll notice that with Chem 1 problems, sometimes they just try to overcomplicate it. We've got a temperature of 98 degrees Celsius. We've got a pressure of 715 millimeters of mercury, and we've got a volume of 121 milliliters. And then, of course, we've got that mass of 0.471 grams. Very similar to what we just saw. So first thing is we're going to use PV equals nRT to solve for moles. So pressure, 715 divided by 760 to go to ATM. I really have 0.941 atmospheres. Volume, 121 milliliters, but divide that by 1,000. So we really have 0.121 liters. Temperature, 98, but we would add the 273.15. So this is really 371 Kelvin. All right, so then step 1, let's find N. PV divided by RT, pressure 0.941, volume 0.121, R 0.08 206, temperature 371. So how many moles do we have in that sample? So we know our pressure, we know our volume, we know our temperature, and that'll tell us that we had 0.00374 moles of gas present. So then second step is, what is the molar mass? So we know that that many moles had a mass of 0.471 grams. So basically we're setting up a ratio, right? If I know that 0.00374 moles had a mass of 0.471 grams, the question is, what would be the mass of 1 mole, right? We're just basically setting up a ratio. But I like the units. Units always do the work for you. So we're going to take 0.471, divide by 0.00374, and I get a molar mass of 126 grams per mole. So that would be the molar mass of whatever that unknown substance was. All right. Okay, so all of the formulas that we've done so far, it really comes down to just memorizing two things. P1V1 over T1 equals P2V2 over T2. That's your formula if you're heating the gas, changing the volume, right? Trying to see what happens to another variable, right? If the gas is heated up to 200 degrees Celsius, what happened to the volume? If the volume is squeezed, what happened to the pressure, right? The other formula, PivNert, is when you just have one set of conditions. And we're either looking at the density of the gas, the molar mass of the gas, or just how much mass is actually present in the sample. But we just have one pressure, one volume, one temperature. So what remains in the chapter is stoichiometry, because you know you got to have stoichiometry for gases. And then we also have to talk about Dalton's law of partial pressures, and that's what's coming next. So this goes back to something we looked at. When we were talking about Avogadro, we had said, okay, if we have two containers and they have the same volume, temperature, and pressure, those two containers, the question, this is what partial pressures is getting to, and this was Dalton, John Dalton. So Dalton's law of partial pressure says that if container A just has moles of hydrogen in it, but then the other container has hydrogen in it and oxygen, right? If they're at the same temperature and pressure, and the two, what word am I looking for? My English is escaping me. My two containers, there we go. Same temperature, same pressure. The containers have the same volume. The idea was, remember, if it's the same temperature, pressure, volume, there should be the same number of molecules inside. Dalton, his theory was that, since gases are mostly empty space, and one of the fundamental parts of ideal gas law is that gases have no attraction or repulsion for each other, which honestly, it stays true because they're mostly empty space. So the gas molecules really don't interact because it's mostly empty space. So the ideal gas law works as long as the gas molecules stay pretty far apart. If we crank up pressure really high, or we decrease temperature really low, in which case those gas molecules are either colliding all the time or they're right next to each other because of how cold it is. When we get to those extremes, then we start realizing that that ideal gas behavior falls apart. But for the most part, the ideal gas behavior stays true. Gases are mostly empty space, which means they're really spread out and far away from each other. So the gas molecules really have no interactions with each other, just the collision. And the collision is elastic, which is a term I remember learning in physics, which is that if that collision occurs, no energy is lost. So those gas molecules just collide and keep going, not like two cars that collide and stop. Those gas molecules, when they collide, they don't lose any energy. They just keep going, and they collide with the walls of the container. They collide with each other. And to the gas molecule, it makes no difference who it's colliding with. It just is a collision, and that just counts as a collision. So Dalton came along and said, okay, well, if we have two containers, same volume, same temperature, same pressure, that means there's the same number of particles inside. And then that means that it shouldn't matter what the particle is, right? So in the first sample, I have only one type of gas, and I'll just be easy. Let's say there's 4 moles, right? I drew 4 gas A, right? So there's 4 moles. In the second container, there's still just 4 moles. 2 of them are A, 2 of them are gas B, but total, there's still only 4 moles. That's Dalton's law of partial pressure. That if I take the partial pressure of gas A in the mixture and I add it to the partial pressure of gas B, then I'm going to get the exact same total pressure as if I looked at that first container. All right, so let me show you how the math works here. It says, so I cut the number of moles for container 1.5. Only the moles of A was cut in half, but then I added moles of B. So my total moles is 4 either way. So that's why the pressure stays the same. The total moles in both are 4. So the total pressure is the same, total temperature, total volume, right? Everything stays the same. So if I look at this question, it says, what would be the total pressure if I have 4.05 grams of nitrogen, 3.15 grams of hydrogen, and 6.50 grams of helium in a container? And that container is 6.10 liters, and I'm at a temperature of 25 degrees Celsius. So here's what we're doing. If we're trying to find total moles or total pressure, let's talk about that first. This is really Dalton's law, would be equal to the pressure due to the nitrogen added to the pressure due to the hydrogen added to the pressure due to the helium. All right. Now let's think about what is our formula for pressure. Pressure is nRT over V. If I use Pivnert and I just divide both sides by volume. So if I think about these 3 different gases, the moles are different, right? Because I have different masses of each, different molar masses. So the moles are different, but R is a constant, 0.08206. Temperature is the same for all 3, 25 degrees Celsius, which of course will convert to Kelvin. And the volume is the same for all 3. They're in a container that's 6.10 liters. So really what's going to happen here to make my life easier is, instead of figuring out the pressure of the nitrogen, pressure of hydrogen, pressure of helium separate, what I'm going to do is I'm going to find the moles of nitrogen, add it to the moles of the hydrogen, add it to the moles of the helium, get my total moles present. And then I'm going to multiply that by RT divided by V, right? So basically what I did is I'm going to factor out the RT divided by V because that's constant. None of that is changing. So instead of doing 3 different Pivnert calculations, I really only have to do one, but I first have to find my total moles present. All right, so total moles, moles of nitrogen. Let's do that one first. We had 4.05 grams divided by the molar mass of 28.02. That'll tell me how many moles of nitrogen I have. So 4.05 divided by 28.02, I get 0.145. All right, now let's do that for the hydrogen. I've got 3.15 grams. Molar mass here is 2.02 for the 2 hydrogens. And the total moles, or sorry, the moles of the hydrogen I get is 1.56. Now let's do helium. I have 6.50 grams of helium. Molar mass is 4. Oops, sorry. Let me squeeze that. So if I take 6.5 divided by 4, I get 1.63 moles of helium. All right, now what I'm going to do is I'm going to figure out my total moles. So I'm going to take 0.145 added to 1.56 added to 1.63, decimal place rule. So we're going to go 3.34 moles total. So now I know my total moles. So this pressure, total pressure, is going to be equal to the total moles of 3.34, R 0.08206, temperature converted to Kelvin would be 298, and then volume in liters, 6.10. So I've got my 3.34 times 0.08206 times 298. The 298 was just because it gave me 25 Celsius, but I added the 273. And then if I divide by my volume of 6.10, I get a total pressure of 13.4 atmospheres. All right. Now, if you wanted to check and you wanted to go through this and use Pivnert for moles of nitrogen and then RT divided by V, and then do another Pivnert calculation with 1.56 as your N times RT divided by V, and then do another one, Pivnert for helium, 1.63 moles times RT divided by V. Then you add them all together, you'd get the same total pressure. This is a little bit simpler because since the temperature and volume is the same for all 3 gases because it's the same container, then what can be simplified is let's just figure out what the total moles are that are present. Use that as the N value, and then that'll give us our total pressure. So that's our total pressure. But really what this was is this is the pressure due to the nitrogen, hydrogen, and helium all added together. And yes, you could always do total pressure this way. All right, so you could, if you wanted to, I feel like it's longer, but you could find the pressure just due to nitrogen using Pivnert, the pressure just due to hydrogen using Pivnert, pressure of helium using Pivnert, and then add the 3 together, but you'd end up at the same place, 13.4. Because temperature and volume are staying constant, and of course R is constant, it seems easier to just figure out your total moles first and then plug that into Pivnert. To me, that seems a little bit shorter. It's long enough as it is. Now, where does collected over water come from, or like where does it become important? If you remember this from intro, this is always when you have the gases that are collected over water or collected through water. Oftentimes, if we do a reaction and we want to collect the gas that's being produced, if you imagine collecting that gas into a container that's filled with air, how would you know in that container what's air and what's gas, right? You wouldn't know. So what typically happens is you have a container that's filled with water and you bubble the gas up, the water is displaced, and then you know that that sample of gas that you've collected is in fact that sample of gas that you produced, right? So it's not like it's air. It's if you're doing a reaction that produces hydrogen gas, then you've just collected that hydrogen gas. So you'll see questions where it says, okay, you've collected this gas over water, or it'll say collected through water. I never understood like why over water, but it's really collected through water. But anyway, here's why this becomes a small problem. When you collect a gas through water or over water, some of the water bubbles up with it and it's in the gas phase. You don't see it. It's not liquid water. It's just water particles that are in the gas phase. So what'll happen is you'll have your container of gas that you've collected, and most of it, let's just say we're collecting gas B, right? Most of your sample is gas B. But inside, you're going to have a tiny, tiny, tiny amount of water that's trapped in there. And it's hard to like know exactly how much you have because it's bubbling up with your reaction, right? But it turns out it's actually not hard to know how much water is there. It turns out that the pressure of water is temperature dependent. So we have tables, and you'll see this in the lab when we do it in lab. It's a giant vapor pressure of water table, and it'll tell you at any temperature you can imagine, it'll tell you the pressure of water that would have bubbled up at that particular temperature. So I'm just pulling my lab manual out for you to see this. So if we do an experiment and we are at 20 degrees Celsius and we collect a gas by bubbling it up through water, the pressure due to water in that sample is 17.5 torr. If I'm at a lower temperature, I'm going to have a lower pressure. Less of it will bubble up. If I'm at a higher temperature, I'm going to have a higher pressure because more of it will go into the gas phase. But it turns out that it's completely temperature dependent. It's like a constant, which is kind of interesting, right? So I know if I do my reaction, I'm at 21.2 degrees Celsius. The amount of water that gets bubbled up is 18.892 torr. That's the pressure. So what does that mean? What that means is that what I'll do is the pressure in the container is really a mixture, and it's typically equal to atmospheric pressure in the room because when we collect gases, we don't pressurize it. Typically, it's just equal to whatever the pressure in the room is. All right, so a lot of times that's called the barometric pressure, but that is the pressure of the entire container. What I'll do is I'll subtract out the pressure due to the water, which again, I'd get right from the table. And that'll tell me the pressure of whatever gas it is I'm collecting, in this case, gas B, whatever it is. So let's put one of these into practice. So we're going to do an experiment and we're going to collect hydrogen gas. And there's that phrase, right? And actually, this is what we do in lab. We're going to collect hydrogen gas. It's collected over water or through water, and we're at 17 degrees Celsius. All right, so that temperature is important because that temperature tells us the vapor pressure of water that's bubbled up in our sample. Because we're at 17 degrees Celsius, we know the pressure due to water is 14.5 torr. So that would have come from that table I just showed you. Now it says the total pressure in the collection jar or in our container is the barometric pressure, which is the pressure in the room, and that is 738 torr. So here's the problem with the 738 torr. So that 738 torr is equal to the pressure of the hydrogen gas that I've collected and a little bit of pressure of water, those trapped water molecules that bubbled up with it. So in order for me to find the pressure of just the hydrogen, I need to do a little subtraction step. I'm going to take the 738 torr and I'm going to minus the vapor pressure of water. Now remember, that vapor pressure of water is temperature dependent. So as long as I know what temperature I'm at, which is 17 degrees Celsius for this one, then I know exactly what my vapor pressure of water is. So I'm going to take the 738 minus the 14.5, and I get 723, and I don't know why I wrote that. Sorry, 723.5 torr. All right. Now on this one, if you're thinking decimal places, let's round that to 724. That sounds good to me, but I'm going to go ahead and keep it, and we'll worry about the sig figs at the end. Okay, so we got our pressure of just the hydrogen now. So if I look at my sample, right, let's assume this is hydrogen, B. That little bit of water in there, that is contributing to the collisions. That's part of the overall pressure. So if my total pressure is 738, but I know the pressure of the water is just 17.5, that would be given, sorry, 14.5, that's given. Then if total is 738, let's take out the 14.5. Then what's left is the pressure just due to the hydrogen, and that would be the 723.5. So that's the pressure just due to the hydrogen gas. All right. All right, so there's our pressure. Now, the question is, what mass of hydrogen did we collect? So this is why we needed to know the pressure of just the hydrogen. Because again, asking ourselves, whoops, what formula? Is it PivNert or P1V1? We just have this collection of hydrogen gas. We're at one temperature, we have a pressure, we have a volume. So we know then that this is a PivNert problem. So if we're trying to find mass, that means we're really trying to find moles. So we had to know the pressure of just the hydrogen to figure out the moles of just the hydrogen. So the pressure was 723.5, but we're going to divide that by 760 to go to ATM. So what I get in ATM is and now I'll round it to 3 sig figs, 0.952. All right. Why are tables not in Kelvin and ATM? That's a great question. Some tables are. Yeah, I'm always kind of dumbfounded by that too. Like, why isn't there just one master periodic table? Like, why would there be any subtle differences with the periodic table? So the question was, why are these tables like the one I just showed you, instead of giving the temperatures in Celsius and the pressures in torr, why not give the temperatures in Kelvin, because that's our standard unit, and the pressures in ATM, because that's our standard unit? And yeah, the answer is I don't know why not, because that would maybe make it too easy, right? So, but I agree with you. We should pick a unit and stick with it. So there's our pressure of just the hydrogen in our sample. Then the volume of the container was 246 milliliters. We divide that by 1,000, it's really 0.246 liters. Now I remember as a student thinking, but wait, if we're kind of mathematically trying to subtract the water, why wouldn't that change the volume? Because wouldn't the space occupied also decrease? And I remember asking my teacher about that. And what you want to think about is, remember, gases fill the container, like they're flexible, the volume is flexible. So that container is 246 milliliters, and the hydrogen gas would occupy that volume. What we need to do to subtract out the water is subtract out the collisions that are due to the water. The gas would still fill that space, right? So we just need to take out those collisions due to the water molecules. So that's why when you have a collected over water problem, it only affects the pressure. That's the one where you have to do a little bit of changing up front. All right, and then temperature was 17 degrees Celsius, but of course we add the 273.15. So we would get 290 with a decimal to keep it as significant to the ones place, 290 Kelvin. Now we can solve. So N would be PV over RT, pressure 0.952, volume 0.246, R 0.08, 206, temperature 290. So this will get us our moles of hydrogen. So 0.952 times 0.246, divide by 0.08, 206, divide by 290, keep 3 sig figs, got 0.00984 moles of hydrogen. And then if we want to do mass, we're just going to take 0.00984 moles. Remember, hydrogen is a diatomic, so molar mass, 2.02 grams per mole. So when I multiply that, I get 0.0199 grams of hydrogen. So not much. So yeah, 0.0199 grams of hydrogen would be the mass of hydrogen that I've collected. Okay, the rest of the chapter is going to be stoichiometry. We are kind of at a good stopping point for today. I'm going to come back on Tuesday, finish. I knew, according to the schedule, like I knew what I'm looking at, chapter 8's relatively short. So I knew I was going to be a little bit behind with chapters 5 and 6 in terms of not being able to finish them in one day. But I know chapter 8 is short, so we're going to make it up next week. But anyway, what I'll do though is, because I'm not technically done with this yet, I don't want to finish it on Tuesday and have the quiz due Wednesday. So I'm going to move the due date for the quiz. So just to kind of give you your due dates, the accurate due dates at this point, like we talked about at the beginning of the first part. So quiz 4, which again is in chapter 5, is due Monday at midnight. Quiz 5, which is going to be chapter 6, instead of having that be due Tuesday next week, let's change it to have you have it until Friday at midnight. So all the due dates here is 11:59 p.m. So I'm going to go ahead and change that due date in the calendar in my courses, so you have a few extra days, just because we're not going to be able to finish it. We've got a couple more problems to do. So we'll finish it on Tuesday. That'll give you till Friday. But most of the chapters done. You can certainly get started with the dynamic study guide, with the worksheets. We'll just save stoichiometry for Tuesday. And if you had intro, you've seen this before, so it'll just be a review. But anyway, that's it for today. I hope everybody has a great weekend. If you have any questions for me, let me know. You too, thank you. But otherwise, I'll see you back Tuesday.